Hello and welcome to the Omnex webinar, ISO SAE 21434, the newly released International Standard for Automotive Cybersecurity. Today's presentation is being conducted by Dr. Juan Pimentel. He is a principal consultant for Omnex with extensive engineering, safety, and cybersecurity experience. Dr. Pimentel has extensive experience also in security and cybersecurity, in operational technology and industrial control systems environments that include oil and gas, petrochemical, and automotive. Juan has participated and continues to participate in various IEEE, SAE, and ISO standards. He is on the SAE Vehicle Electric Hardware Security Task Force and the SAE ISO 21434 Automotive Cybersecurity Task Force, as well as ISO PAS 21448 Standard Task Force. During this webinar, if you have any questions for Juan, please enter them in the Q&A box, and he will get to them to the best of his ability at the end of the webinar. The webinar is being recorded, and someone from Omnex will reach out to you with how to access the recording and the slides after the webinar. So just wait for someone from Omnex to contact you. All right, Juan, you can take it away.
All right, thank you very much for the introduction, Miles. Can you see my screen all right?
I am not seeing your screen or your camera. You might want to turn your camera on and share your screen.
How about now?
I can now see the PowerPoint.
All right. Do you see it full screen now?
I see the full screen. You want to turn your camera on? There you go. Go ahead.
Okay, so good morning and welcome to the Omnex webinar on the new release standard ISO SAE 21434. So the first few slides is an introduction to Omnex, some of the services we provide and the locations around the world, okay? And also a little bit of history about the company. We started out 35 years ago in the area of quality, but gradually we started covering additional areas. And the two areas that are pertinent to this particular webinar are safety and cybersecurity. But we also are working on other areas like medical devices, semiconductors, and industries like that. We have offices in various parts of the world, as you could see, primarily in Europe, India, and China. As I mentioned, the target markets are quite varied. Myself, I am concentrating in the automotive area, but as you could see, we also have expertise in aerospace, semiconductors, medical devices, electrical vehicles, and general automation. We do have a new website for the area of electric and autonomous vehicles, which is shown on top. And of course, the older website, it's still available. There is a slide about my background. I think Miles already went through this, so I'm going to skip this. And also, this is the summary of the webinar that was released for marketing purposes. So I'm not going to go over this. I presume that most of you have read this. So let me just move to the actual topics that we'll be going over today. I will provide a context for several standards for vehicle cybersecurity. But obviously, we will concentrate on the new released international standard, which is a cooperation between the ISO and SAE, and the number is 21434. I will go over some commonalities of functional safety and cybersecurity, and discuss the structure of the standard and the main key features. I will also concentrate on explaining that there are two ways to characterize risk in this standard, called CAL and risk value. I will emphasize some things that are unique to this standard, for instance, the so-called continual cybersecurity activities, and also go over some of the addenda that it's incorporated in the standard itself. I will conclude the seminar with giving you Omnex position in terms of where the industry is today and the key challenges implementing this particular standard. And the conclusions will be at the end. So one of the main things I'd like you to make clear is that when this standard was being developed, there were other standards already in place. In other words, 21434 is not the first automotive standard. There has been several efforts, and this diagram summarizes some of those. As you could see, there are some ISO standards, like on top you have 2700 series, and then on the top left you have the 20007, and then you have standards which are noted by X dot. These standards come from the ITU, which is the International Telecommunications Union from Europe. And as you could see, these standards are also correlated to the diagram on the bottom. The diagram on the bottom shows the vehicle, but we're talking about just three main components of the vehicle, in addition to the communication network here. So the top left component would be the OBD2 port, which is the onboard diagnostics. And then on the center and top, you have the computing, which is called an edge node, which is an interface to things external to the vehicle. And then on the right side, you have the trusted processor module, which is, think of it as the hardware aspects of cybersecurity in the vehicle, okay? So correlated to that, you have several efforts, not only by ISO, but even SAE. For instance, SAE on the top right has a standard called J3101, which is again related to the hardware cybersecurity of the vehicle. So in summary, as you could see here, the 21434 standard is not the only standard for automotive. There's a bunch of them. Particularly, I will also go over a UN's ECE, which is a United Nations recommendation for cybersecurity. And sometimes it's called WP.29. I will go over that a little bit because it has a bearing on this standard 21434. All right, so this new standard then, as I mentioned, it's fairly new. It was released in August of this year, and it's consistent with already established functional safety standards. Particularly, I'm talking about ISO 26262. This standard, 21434, supersedes an earlier document called SAE J3061. And it's based on a product lifecycle. The life cycle is concentrated on the safety life cycle and also on the cybersecurity life cycle. Okay. The main purpose on the standard is to, from the very high level, is to provide a vocabulary, a set of objectives, and more importantly, some requirements and guidelines as the foundation for the common understanding throughout the supply chain. which means that it's not only applicable for OEMs, but also tier ones and even tier two organizations. And this standard will enable organizations to perform several things. For instance, to define a cybersecurity policy and processes, to manage the risk, and to foster a cybersecurity culture. Out of this, I like to emphasize the notion of processes. So the standard talks about many processes, and processes really are defined as anything that needs to be put in place by the organization to implement this standard. On the right side, you have some main benefits of implementing this standard. And the list is actually quite long, but as you could see, this would be like top level benefits. First of all, you have a common terminology, and this is particularly true for cybersecurity because cybersecurity has a long history in the area of security in general. So several industry segments use different terminology than, for instance, automotive. Okay, so it's very important to have a common terminology. It provides also an industry consensus about certain things, particularly on the risk identification and risk treatments area. Also, it sets minimum criteria for the cybersecurity engineering and creates a key reference. In addition, it builds trust and also provides what it's called a framework for cybersecurity engineering. So what it is to be expected from this standard? So this standard was built to be used as a baseline. The baseline would be for vehicle manufacturers and suppliers, for cybersecurity organization and governance, and also for cybersecurity engineering throughout the life cycle. In addition to also the post-production processes and lessons learned, training and communication, and to distinguish itself from other cybersecurity standards. For instance, IT stands for information technology, also for manufacturing and even cryptography. So this baseline is very useful to compare a basic implementation of automotive cybersecurity according to this standard and use that as a baseline for additional incremental implementations of maybe additional standards or additional requirements from the organizations, from the stakeholders. This standard applies to all vehicles EE, and EE here stands for electrical and electronic systems. Excuse me. So in that context, the application of this standard is very similar to functional safety because functional safety also targets electrical and electronic systems, including their components and interfaces. And as I mentioned before, it's a requirements-based standard, meaning that it actually defines many requirements that are expected to be implemented by the OEMs or suppliers. And this is an example of one requirement. So in the standard, you have things like RQ 0502, which means that this is a requirement for clause 5. And clause 5 in this standard is about the organizational cybersecurity management. And 2 would mean that this is the second requirement. Okay. So this particular requirement, for instance, says that the organization shall establish and maintain organization-specific rules and processes to do a couple of things: enable the implementation of the requirements of this document and support the execution of the corresponding activities. So this is a requirement that basically says you need to have processes. And in addition to these processes, rules to achieve these two goals, A and B. And here are a few examples or notes, which is additional considerations or explanations about this particular requirement. So this is what is meant by a standard being requirements based. It has a bunch of requirements such as this one. So what's in scope of this standard? So again, it specifies requirements for the cybersecurity risk management for electrical and electronic systems engineering through the concept developing and decommissioning to decommissioning. Okay. In addition, it provides a cybersecurity process framework. In other words, the framework to talk about processes and the common language that I pointed out before a couple of times to communicate cybersecurity risk. And it applies to all vehicle electrical and electronic systems and their components, including interfaces. However, some stuff is out of scope. So for instance, specific technology or solutions are out of scope. So this standard does not provide the how to do things. If you will, it only provides the what it should be done, but not the how. The how is outside the scope of this standard. However, it does have few recommendations here and there on some aspects on the how, but the standard does not prescribe specific technology. In addition, what's out of scope is the requirements around remediation methods. Again, this would be another example of the how. Also, it does not address requirements for telecommunication systems. It only addresses communications inside the vehicle. In other words, in-vehicle communication systems. So telecommunication systems will come outside of the vehicle. Also, it does not address requirements at the connected back office. So the cloud would be one example of that. It does not address, for instance, requirements for electric vehicle chargers or requirements for autonomous vehicles. So I mentioned that this standard was developed taking into account another standard from functional safety and adopted few things in common. So this slide goes over these things that are common or fairly common, or at least analogous between functional safety and cybersecurity. So I call these commonalities. So even though the details are different, obviously there are some commonalities, and the first commonality is that both standards use a risk-based approach, which means that they talk about a safety risk as well as a cybersecurity risk, of course. And these conceptually are the same. However, the way you characterize this risk and you evaluate the risk and you use this risk is different. But conceptually, it's the same notion. Another commonality is in the area of determining hazards and threats. So you could actually liken or model, if you will, threat as being a type of a hazard. So a threat scenario would be equivalent of a hazard in functional safety. Okay. So as I mentioned before, whenever you talk about safety hazards, then the equivalent concept in cybersecurity would be cybersecurity threats or threat scenarios. And they follow a similar analysis. So again, conceptually, this is the same, but the difference is the details and the techniques that you use for that. And even the way you evaluate them is going to be a little bit different, okay? Still another commonality is the area of risk determination. So for instance, in functional safety, you have the so-called automotive safety integrity levels, which is one way to really classify the risk levels in functional safety. And you probably know, or for those of you who are familiar with functional safety, you have several levels going from ASIL A, B, C, and up to ASIL D. Similarly, in cybersecurity, we have what is called cybersecurity assurance levels, which goes from CAL 1 and to CAL 4. And the last commonality would be in the area of risk treatment. Again, the concept is the same, okay? The idea being that if the level of risk is not acceptable, then the risk can be reduced through certain techniques called risk treatment. The nature of the techniques are different, but the concept remains the same. And here is a table that summarizes some of the stuff that I've been talking about and clarifying a few other things. In particular, for instance, the concept phase, there is a similarity between the two standards. They both have a concept phase. The item definition is the same. The safety goal in 26262 has a commonality in 21434 with cybersecurity goal. There is a functional safety concept. There is also a cybersecurity concept. There is a technical safety concept, and the concept is similar, except that in 21434, they have replaced the word technical by refined. Okay, so it means the same thing, except that they have chosen to use the word refined rather than technical. And then the ASIL is equivalent to a CAL. There is a process called HARA in functional safety, which is hazard analysis and risk assessment. In cybersecurity, we have a similar process called TARA, which stands for threat analysis and risk assessment. The requirements in terms of hardware and software architectures are similar, not exactly the same, but they're similar. The risk-based approach against is similar, as I pointed out before. The safety mechanisms are replaced by cybersecurity controls. The concept is the same. The name changes, perhaps for historical reasons. Historically, in cybersecurity, these mechanisms have been called controls, and that notation still remains. There is a safety case in functional safety, and there is a cybersecurity case in 21434. Again, the way you apply the standards and then you review the work products, including the audits and assessments, they're the same for both standards. The topics about system integration and testing, they're similar, and so are the verification and validation. This is the structure in general of the final standard. I'm going to go over the top part and the lower part separately because you may not read this very well. So I'll comment on the top portion and then the lower portion in this slide and the next slide. So the clauses 1 through 4 are really introductory. The main clause in terms of, the first clause in terms of the requirements actually begin with 5, okay? So clauses prior to clause 5 then do not have requirements, just general considerations, vocabulary, definitions, and stuff like that. So clause 5 and 6 are very similar because they deal with management. And 5 deals with management at the organizational level, which means that it is independent of the project or a product. You address things like cybersecurity governance, culture, information sharing, and cybersecurity audit. The clause 5 deals with project dependent, which means product dependent also. So in this standard, project and product could be used interchangeably for the most part. As you could see, this has topics such as the responsibility for cybersecurity functions, the planning, the tailoring of this standard, the reuse of components, how to deal with a component out of context. And some of these, by the way, is very similar to functional safety, okay? And some of these are new or different. And then off-the-shelf components, how to do the cybersecurity case and the assessment, and how to do the release for post-development. Clause 7 deals with distributed cybersecurity activities, which means that this is a clause that needs to be taken into account whenever there is joint development. For instance, an OEM working with a tier 1, that's a typical scenario, but it could also be a tier 1 organization dealing with a tier 2 with a supplier. Okay. Clause 8 has to do with the so-called continual cybersecurity activities. And this is something that is different from functional safety and something that distinguishes cybersecurity from safety. Because in cybersecurity, after the product is released, you still need to do very important activities. For instance, monitoring the cybersecurity and doing event evaluation, vulnerability analysis, and management. In terms of the product lifecycle, you have the 3 main phases here: concept phase, product development phase, and the post-development phases, which are in clauses 9, 10, and 11, and 12, 13, and 14. The concept phase in this standard is very similar to functional safety, meaning that you deal with the topics such as item definition, developing the cybersecurity goals, and producing the cybersecurity concept. Very similar. What's different is product development phase. One of the main differences, as I will point out later, is that in 21434, the V model is not used explicitly. And the reason for that is that in cybersecurity, the expectation is that there is not much hardware development. If there is, it's very little. It would be mostly software. And therefore, a lot of the system, hardware, and software development that needs to take place is referred back to the functional safety standard 26262. Okay, so 21434 concentrates on some aspects of the design, which is generic, 1041 here, and then 1042 deals with integration and verification, and 11 is the validation. The post-development phases are the production, the operations and maintenance, and then the end of cybersecurity support and the decommissioning of the product, of the vehicle in this case. And the last clause, 15, is really the methods that are used to do the TARA. Okay, so this is the method that this standard recommends. Okay, there are many methods, some of you may probably know, but this is the one that's picked up by the standard that's applicable for automotive cybersecurity, that deals with these particular topics: asset identification, threat scenario identification, impact rating, attack path analysis, attack visibility rating, risk value determination, and risk treatment. Okay, so the next few slides will talk about the key features. Obviously, it is not expected that I cover all the details of this standard. We have a class at Omnex that actually takes 5 days to go over this standard. So in 1 hour, I can only talk about the main key features. First of all, I pointed out that the concept phase is similar to ISO 26262. It's not identical, but at least conceptually is the same. In the product development phases, there is a big difference. As I mentioned earlier, the main difference is that in the product development phases, the V model is not used. So the framework that's used in this standard, which is the same as in functional safety, is a process framework. So 21434 provides a high-level process framework, recognizing that many other standards and guidelines are available for product development. So again, this may be a bit of the challenging portion to implement this standard, because this is not the only standard that's necessary to implement automotive cybersecurity. There are other ones like 26262 and ASPICE. Also, there is a unified model that is presented here, which can be iterated or refined as required by the specific product under development. This falls under the category of tailoring this standard for specific cases. Again, one feature of this standard that's different from 26262 is that there is no separate requirements for system level design, for hardware design, or software design. And this is unlike ISO 26262, where we do have this separation, okay? We don't find that here, at least not explicitly. It does not mean that there is no system level design, hardware level, or software level. It just means that this standard does not address those explicitly and refers back to ISO 26262 to consider that standard if you need to do design at the system level and partition that into hardware and software levels. There are additional specific requirements for software development. Just a few things. So out of these three, the only thing that this standard gives additional recommendations is for the software aspect. The validation is a distinct activity to verification, with specific objectives, and therefore it has its own clause, which is clause 11. The post-development phases are somewhat similar, except that the emphasis are a little bit different. For instance, the unique requirements in terms of the post-development phases are that there is a section on incident response, which is very important, cybersecurity incident response. And another one is on updates of this standard. This diagram illustrates some interactions between the standards, particularly the concept phase, which is clause 9 on the left side, and clause 15, which are the methods to do the threat analysis and risk assessment, as you could see. So think of this as perhaps a high-level definition of the process at the concept phase. As you could see, you begin with the item definition, and then move on to the next section, which is to determine the cybersecurity goals. And finally, you develop the so-called cybersecurity concept at the bottom. But the cybersecurity goals is, as you could see, decomposed into three elements. One of them is really the TARA, and that is correlated to the TARA section in the methods, which is clause 15. But after you determine the risk level, the next thing to do is to perform what is called the risk treatment. And that's in requirement 9.4. After that, you determine the cybersecurity goals, which is requirement 5. Okay. As you could see, there is a correlation between the concept phase and the clause 5, which deals with the specific methods to do the TARA. Now, another big difference between this standard and functional safety is that there are two ways to characterize risk. In functional safety, there is only one way, which is equivalent to the top one, if you will, which is CAL. But in cybersecurity, there are two ways. And you may be wondering why there are two ways. And the short answer is that the risk levels in cybersecurity are much more dynamic than that in functional safety, which means that it could change. A good example is that whenever a issue is detected, okay, then the cybersecurity level changes, and whenever the issue is fixed, it changes again. So, and that could happen even after the vehicle is put into circulation, okay? So it's not a constant value, but it changes. So therefore, this standard has divided the risk characterization into two. One, which is static, if you will, that's CAL, that only applies up to the post-development phases. And one that's called risk value, which is dynamic. It applies through the whole cycle, even post-production or operation until decommissioning, okay? So this is the reason why you have two risk levels. Also in this standard, sorry, in this slide, as you could see, I have actually put the detailed way on how to determine the risk level. And basically, if you recall the notion of risk in general is a combination of two things. Number one is the impact of the consequences on the right side. Sometimes this is called the severity or consequences, okay? And the other one is the probability of those consequences or attacks or actions, if you will. And that's called attack probability. So therefore, these tables is really an estimation of this notion, okay? So the estimation of the impact, well, it's called impact, and it's done by 4 levels, as you could see. They're severe, major, moderate, or negligible. And the estimation of the attack probability, we have 2 estimations. The top one, you estimate the probability in terms of the so-called attack vector. In the lower table, you estimate this probability in terms of what is called the attack feasibility. So as you could see, attack feasibility conveys the notion of probability also. And you read out the risk level. In the top, it's called Cal 1 through Cal 4. And the bottom is just a number, okay, that goes from 1 to 5, as you could see, okay? So how do you use Cal? The way you use Cal and risk values are different. Cal is a little bit similar to ASILs, but not exactly, because remember, Cal is static. It doesn't change. So Cal has been used to determine the level of rigor to performing cybersecurity activities. So it's a high level type of measure. And by the way, let me clarify also that Cal is optional. However, I do expect that most organizations will use Cal because it does have some definitive advantages. But the standard has decided that you do not have to apply it if that's the decision of the organization. The middle bullet point is the main one that specifies how can Cal be used. So it can be used to select methods used for the development and verification, methods to identify weaknesses and analyze vulnerabilities, and simply approaches for the cybersecurity assessment. And a good example is this table that we have here. This is a table that talks about some of the type of activities that are performed, and these activities have what is called independence level. So independence level have to do with the degree of independence about who is performing these particular activities. And they're classified by I1, I2, and I3. I3 is the most stringent, which means that the person who is performing the activity has to be an independent, perhaps from a different department or different organization. Whereas I1, it could be simply by a different person in the same organization or in the same group. And I2 is, of course, intermediate. So as you could see, Cal 4 is the most stringent because it requires I2, and I3, depending upon the type of activity that you're performing. And of course, Cal 1 is the least stringent because it requires simply I1. And in terms of the assessment, it doesn't have any requirements whatsoever. Let's move on to the other estimation of risk, which is risk value. I mentioned that this is more dynamic, more accurate also. The purpose can be used for different things. For instance, to support criteria for decisions on risk treatment, including the selection of controls. Also, the prioritization of risk for treatment, reporting stakeholders, and monitoring of the risk. So as you could see, these are important ways where the risk value can be used. And this is actually a requirement as opposed to a recommendation, which is the Cal. Again, I reproduce the way that the risk value is estimated in terms of the attack feasibility rating and impact rating. And it says that the organization is really ultimately responsible to determine this risk matrix. The standard recommends this risk matrix, but ultimately an organization is allowed to use a different one as long as they provide a rationale for it. Let's talk about a key feature of this standard, meaning that this is unique to this standard and not shared with ISO 26262, for instance. And that would be this clause 8, that means continual cybersecurity activities. And that means that even after the post-development phases, particularly during the operations, okay, what you have, so in clause 13 here, okay, you have things that the activities are the following: cybersecurity monitoring, event evaluation, vulnerability analysis, and management. And this is very important, as it's illustrated actually in the next diagram in a more conceptual way. So again, clause 8, sections 3, 4, 5, and 6 deal with cybersecurity monitoring, first of all, where you need to do a triage of this information and determine whether or not this, whatever you're monitoring constitutes an event. If it is an event, you have to manage it appropriately. However, the event may be further propagated and then you need into an incident. And if that happens, you need to perform what is called incident response, okay? In addition to that, you need to perform a vulnerability analysis and to manage such vulnerability and go back and redo your TARA. The TARA, I explained that it was part of the, not part, but correlated to the concept phase. After the concept phase, you do the TARA. But this diagram shows that as a result of these continual cybersecurity activities, you may require to do the TARA once again because of some events that has happening. Now, at the end of the standard, there are several addenda that was included for illustration purposes, okay? And this is very useful to take into account. For instance, you have an addenda or addendum actually about CALs. Also a classification scheme so that you will actually adequately protect against unknown threat scenarios. The addenda also talks about tables for impact ratings, feasibility rating, and actually some actual matrices for the risk determination that I mentioned earlier. Also, this leverages the static elements of risk such as impact and accessibility, and a use case scenario where it illustrates in very detailed fashion how to apply this standard for this particular use case. This use case is illustrated in the next slide, which is a headlamp system. It used to be in the past, many years ago, that headlamp or headlights, if you will, were very simple. What you had was the lights on the right and simply switches on the left. And some of you may recall this, but you simply operated the switches, you turn the headlights on or off. Nowadays, it's no longer done that way. You have a sophisticated system where you use a body control ECU, a controller. In addition, you introduce some actuators to operate the lights, okay, which are electronic switches basically. And also to improve the performance or benefits, you introduce a camera, for instance, for sensing the light conditions. So that will constitute what's called the new headlamp system, a new and improved headlamp system. However, in terms of item that we talked about earlier before, you need to consider other aspects. So in this particular example, you have a gateway ECU, which is as the name implies, the gateway between this body control ECU and other ECUs in the system. In addition to that, you may have a navigation ECU, which is connected to a cellular network or a Bluetooth network, or even a Wi-Fi network, which is not shown here. In addition to a connection to an OBD2 port connection, which is used for onboard diagnostics, which is important. So depending upon your design, you may need to include some of this as part of the item or outside of the item. So that's part of the design. So this particular addendum explains how to apply the standard in the context of this particular use case or example, if you will. So moving down to other aspects of the standard. So what is the industry today in terms of this standard? Well, first of all, this standard was just published. However, there are a few versions of this standard, I mean, older versions that has been around for about 2 years. So industry has been becoming aware of what's happening in terms of accidents and also in terms of this standard or related standards. For instance, SAE 3101 and this WP.29 that I talked about earlier. Again, I'm going to be brief about here. The WP.29 has a section 5 on approval, which has some important information. And the most important one is the fact that this standard, okay, it says that shall verify by means of document checks that the vehicle manufacturer has taken the necessary measures relevant to the vehicle in terms of collecting and verifying information, documenting the risk assessment, implementing appropriate cybersecurity risk measures, detecting and responding possible cybersecurity attacks, and logging data to support the detection of attacks. Now, the comment here is that some of these can be part of the cybersecurity case of 21434, okay? Section 6 is very specific, and this one is very important. It says that the manufacturer has to have a certificate of compliance for a cybersecurity management system. This is very critical. And much of this, again, can be implemented by implementing 21434. Not the whole thing, but much of this particular requirement from WP.29. There is also section 7 on other particular specifications. Again, these are detailed requirements for this cybersecurity management system and also for vehicle types, okay? Again, this could be implemented as part of a cybersecurity case of 21434. So moving on with where is the industry today, I would say that the industry is consolidating cybersecurity in general. So it's digesting what's happening in terms of accident, in terms of standards, not only 21434, but additional standards I mentioned. And talking about things related to the strategy of implementing, for instance, using trust anchors like TPM, which is a trusted processor module. Talking about secure architecture frameworks, for example, AUTOSAR. Talking about a PKI infrastructure. Talking about new services, for instance, for cloud protection. And then, of course, using standards such as 21434. In addition, incorporating what is called secure by design, which is promoted by 21434, except that 21434 does not cover everything that is to be covered, okay? And these are examples of the security principles on the right side that I'm talking about that you need to take into account, okay? 21434 does cover some of this, but again, it is not comprehensive. There are key challenges in implementing this standard or implementing automotive cybersecurity in general, okay? The first challenge is that automotive cybersecurity is different from enterprise IT, or even different from IT, which is the information technology cybersecurity, and also from IoT, which is Internet of Things. So automotive is very specific. So anytime you talk about threat models, attack surfaces, attack vectors, vulnerabilities, or controls, these are tailored, if you will, or specific to each particular segment area of industrial area. Also, implementing security by design, we need to be on target because some of these techniques are very generic. And the target here is to target it to your particular product. Still, other challenges include the implementation of standards, knowing that 21434 is not the only one. There are additional standards. For example, you may implement simultaneously 26262 or jointly, if you will, and 21434. Still, another one is to achieving an appropriate level of defense and protection. Okay, that has to do with the vulnerability analysis, penetration testing, and ongoing defense and protection. So that has to do with the degree of, again, defense and protection. Bullet or section E here has to talk about integration of standards and tools. In addition to 21434, I mentioned about ASPICE, and even ASPICE has released a new document, by the way, that is called ASPICE Cybersecurity, which addresses some of the issues of 21434. It's not a replacement. It's an companion standard, if you will, to 21434. Okay. So what does the industry need to do today in terms of this particular standard? Well, obviously, this is the recommendation from Omnex. Point A here is to do or participate in training, building competency in terms of cybersecurity and safety engineering at their organizations, including quality assurance. And the recommendation is to start now. Do not delaying it, okay? And as you will see later on, Omnex has a large portfolio of courses involving cybersecurity. Another thing that is recommended is to incorporate the needed changes in the process flow. In other words, you may have flaws in the organization, processes, I mean. You need to either adapt those processes for cybersecurity, or if you're new to cybersecurity, create new processes. And there are some challenging aspects when you talk about processes involving threat models, risk determination, controls, management of the processes, and also using tools. You need to determine what can be done in-house versus external. And the last recommendation is do not procrastinate. Again, as I mentioned, Omnex has a series of courses. These are a long list of courses related to cybersecurity. As you could see, we've been working on this for actually a couple of years now, because we had access, me being a member of the committee, the United States representation, okay, SAE representation to this standard. We had access to early versions of this standard. So we had a goal of developing, as you could see, several courses, not just one, related to cybersecurity. So what can you do next? Can we do next? Well, in terms of infrastructure, there are software tools to help you analyzing some of this. The software tools are varied. I mean, these are some aspects of the tools. For instance, it could help you with modeling analysis tools. The TARA, which is very important. They're also related to the design and development, like ODESAR could be another tool. And currently, Omnex is working on a TARA tool that interfaces to other enterprise tools that we have. And this will be one example of one tool that we have, which is called EWQ IMS for enterprise-wide quality information management systems. And this tool has some quality aspects. We're implementing security aspects on top of safety aspect that has been done. So obviously this example here deals with some security. We are nearly finished the implementing of the cybersecurity into this tool. you could call Omnex for the details on when this will be released. So here you have few aspects of the tool dealing with cybersecurity. In terms of strategy and implementation, this is some of the recommendations that we do have for customers. Do a gap analysis, okay? Implement quality standards like IATF, and then implement some appropriate automotive software standards like ASPICE, and of course 26262 and 21448 in case you're dealing with autonomous driving systems, and of course 21434, which is correlated to this standard SAE, which replaces actually J3061, but also other standards like I mentioned 3101 for 21434. I mentioned that there is a new document on ASPICE cybersecurity that complements but does not replace 21434. And then you need to concentrate on several aspects of the implementation, such as strategy and the planning of it, which involves risk analysis, the TARA that I mentioned before, the cybersecurity concept. So this is basically implementing various aspects of 21434. So in concluding this particular webinar, I'd like to say that there is a new international standard for cybersecurity engineering that is process-oriented and risk-based, and it's available as of August of this year, so it's fairly new. The processes are very similar to ISO 26262. So if you have experience with 26262, that experience will be very helpful for 21434. There is no separate requirements for at the system level, hardware level, and software levels, unlike ISO 26262. Also, the risk management greatly differs from safety. So we have two ways to estimating the risk, as I mentioned before. Static risk, which is CAL, and dynamic risk, which is called risk value. There is clause 8, which is very specific and unique to cybersecurity, which is entitled Continual, because it continues even after the product is released. In other words, after the vehicle is in operation. There are some unique requirements, I would say, from this standard, dealing with monitoring, event evaluation, vulnerability management, and also incident response and updates to this standard. Now, the organizations need to perform many activities in order to really implement this standard for the safety of your products, okay? It is recommended that you implement the standards in an integrated fashion with other standards, adopt the safety by design paradigm, and then implement the processes defined by 21434. And the final recommendation here is that you start today, perhaps with training and gap analysis, and moving on to the other recommendations that was stated earlier. All right, with that, I'm at the end of the webinar, so I'd like to see if you have any questions. And so I'm going to go into the Q&A to read some of the questions that was asked, okay? Okay, so there's one standard here. It says, I would like to understand the relation between ISO 21434 and SOTIF. Okay, so the correlation is there, but it's not a very strong correlation, because it was stated that 21434 does not deal with autonomous driving systems. And yet, think of SOTIF as providing a attack surfaces that need to be taken into account. So I would say that the correlation is very strong, excuse me, only in the area of interfaces, rather than deep down in the area of the automation or the autonomous driving systems. Another question here is, how does an event that causes a loss of a vehicle function classified as part of the severity level described? Okay, not connecting ratings and categorizing to an event that affects vehicle-related function. Okay, let me see, there are two parts of this question, so let me address the first part. So again, event monitoring or information monitoring, first of all, is part of the standard. And then after the triage, you need to determine whether or not that information that you monitor constitutes an event. So that event may cause a loss of vehicle safety function, okay, classified as part of the severity level described. Okay, yeah, this is a good question. Definitely, it does not affect the CAL that I talked about. It could affect the risk value, because the risk value does monitor things like this. So remember that I showed a slide that whenever you do this, and whenever an event is detected, you need to redo the TARA. And once you redo the TARA, then it will affect the severity level. In other words, you will need to evaluate the risk value one more time. Okay, so that's the connection there. Okay, let's see if I have another question here. If I had a conflicting meeting, oh, sorry, that's not a question. The question is whether or not the recording it will be available. Yes, I believe that it was taped. It will be available. You need to contact Omnex for that. There is another question whether or not we provide a certificate. Yes, we have a, not all the courses, but we have a certification class, by the way, a 5-day class. So some of our courses are certification courses. The requirement is that you need to pass an exam at the very end of the course. And secondly, the certification courses tend to be a little bit longer than other courses. We have 2-day, 3-day, and 5-day courses. So the certification courses, not all of them, but most of them are 5-day courses. Will a copy of this presentation be available? Yes, you can contact Omnex for that. Another question. I'm going to answer 2 more questions, I think, because of time. Okay. Let me answer this question right here. It says, between ISO 21434 and ASPICE, and in parentheses on the ASPICE, it says cybersecurity. Which one is better? It is complementary. Remember that ASPICE is automotive software, so it deals with software levels. So I would say that it's complementary. Think of 21434 as being an umbrella standard, okay? And ASPICE addresses only the software aspects associated with cybersecurity. So in that sense, it's complementary. Still another question is, will ISO 27000 series, particularly 27001, be useful for 21434? I believe there's a mistake in the typo here. Yes, it will be useful, but at a very high level, because 27000 deals mostly with IT cybersecurity. So yes, it is useful, but I wouldn't say that it is directly relevant at the very detailed level, rather at the high level. Okay. Let me answer one last question here. How WP.29 differs from ISO 21434? An OEM needs to comply to both. So this is a great question. It differs in many ways. Number one, WP.29 is a regulation rather than a standard. So that's a big difference. Secondly, WP.29 only applies for vehicle manufacturers. In other words, only OEMs. Does not apply to tier 1s, tier 2s. However, having said that, it does not mean that tier 1 and tier 2 are out of the loop for WP.29. It means that they have to cooperate with the OEMs to meet the standard. And thirdly, WP.29 has two major points or sections. One is the management aspect, and the other one is the software over-the-air updates also that I didn't have a chance to mention explicitly, all right? So it is quite a bit different. So the second part of the question was that does an OEM need to comply to both? Okay, the answer is that if you're a European manufacturer, yes, you have to comply with the standard. An American manufacturer will have to comply only if you sell products in Europe, and not strictly in the US. So that's one way to answer this question. In terms of complying with ISO 21434, it's an industry standard that I would expect you are not really forced to implement the standard. It's mostly an industry-wide requirement. So in other words, it will become a ad hoc standard that will be implemented only because there is, in the industry, there will be agreements between the OEMs, and they ended up that their requirement, this standard, in order to do businesses with one another. Okay, so that's will be the difference. All right, with that, then I'm going to stop the webinar, and thank all for the questions and also your participation. With that, I'd like to see if let's see. I think I could just stop sharing now. So thank you.
Thank you, everyone. Take care.